Okay, so now we're just going to have a look at some single slit diffraction. So as you can see, we've got our single slit here, so it's a nice wide one just for this. And we've got our incoming wave like this. So you can see it's got a coherent wave. So now our wave's reached our slit, there's going to be a diffraction pattern. But before we draw that, what we're going to be doing now is assuming that this is going to our first dark fringe. Okay, so we're going to our first dark fringe. So at the first dark fringe, or to make this easier to see, what we're going to do is we're going to split our wave up into 8 different points. So we're going to imagine that we've got a wave coming from each of these 8 points. So all these waves have come into our slit, they've been diffracted, and they're all moving off towards where this first dark fringe is. Now if we're getting to our first dark fringe, we know that there's going to be destructive interference. So the waves are going to be cancelling each other out. So what we're going to do at this point is represent each of these with an actual wave. So just to show the difference in the path length, this one at the bottom here will have travelled a full wavelength at this point, but then all of the rest will have travelled different fractions of a wavelength when they get to this dark fringe. So this one at the top here has travelled a full wavelength shorter distance than the one at the bottom. But what we can do now is if we take this one at the top and we compare it to one that is halfway down, the difference in path length between those two is half a wavelength. So if there's a path difference of half a wavelength, we know there must be destructive interference. And then if we take another pair that is separated by a distance of half the slit width, then those will undergo destructive interference. And if we take the third one and then take the one that's paired with, we can constantly find that if we pick one that's half a slit width apart, there will always be half a wavelength difference. So if we go back to the phasor model and we give each of these an arrow that we're going to assign it, and we follow those arrows round along each of these paths, because they're all got slightly different path lengths, they're all going to have slightly different final state. So again, we see that this one and this one here, so the top one and the one halfway down, are opposite, so will cancel out. The second one and then the one halfway down again, opposite, so they cancel out, and so on. So if we add all of those up, tip to tail, we've shown there that overall, when there's a difference in path length of one wavelength across the slit, we're going to get destructive interference. So what we can do then is we can start to construct a diagram to actually show this. So here we've labelled on our slit width, which is A. So our slit width A, and what we've worked out is that the difference between the wave at the end here and the top is one wavelength. So we can label lambda here. And then we now know we've got this bit as lambda, we've got our angle theta here, but we can also use our similar triangles to equate that with this here. So we've also got theta here, so we've got a right angle there. So from that, we can use this to then try and work out the width of the central maximum. So over here we've got our lambda, so we can give the wavelength in terms of A and theta. So the wavelength is going to be A sine theta. And if we were to do this for successive fringes, we could then say that for the first fringe, it's just going to be lambda equals A sine theta. For the second dark fringe, it would be 2 lambda equals A sine theta. So what we can do is, for this one, we're going to use m for the order of the minima. M lambda equals A sine theta. Okay? So we also know that the angle theta here is going to be the angle from the point at the center. So the line from the center of the slit to the center of the central maximum, the angle from there to the first arc minimum will also be theta. So we can also say that because that's from half of the, or from the center of this bright fringe, we know that this bit here is going to be W over 2. So we know the distance from the slit to the screen is D. So we can then say that tan theta is going to be the opposite over the adjacent. So it's going to be W over 2 over D. Now, as we looked at before, for small angles, which this would be, tan theta is approximately equal to sine theta. And we know that sine theta is going to be equal to lambda over A. So we can put these together with W over 2 over D equals lambda over A. And we can rearrange this to get our expression for W. So we end up with W equals lambda D, or 2 lambda D over A, which is our expression for the width of the central maximum. And so we've got there by talking about the phases of the incoming waves to show that at this point where there's a dark fringe, then there must be a path difference of one wavelength at either end of the slit, and then we've used that and some geometry to then show that the width of the central maximum must be 2 times the wavelength times the distance to the screen divided by the initial slit width.